Hi everyone. In this video, we're going to explore a core concept in bioinformatics, k-mers and minimizers, and how minimizers help optimize k-mer storage in sequence analysis. Whether you're new to bioinformatics or just need a refresher, you're in the right place. Let's start with the basics. What is a k-mer? A k-mer is simply a substring of length k that is derived from a biological sequence. For example, in this sequence here, we can extract 5-mer like TACGA. K-mers are commonly used in sequence comparison by focusing on exact matches between short, fixed-length segments. This approach makes it possible to efficiently identify similarities or differences between two sequences without needing complex alignment algorithms. We have here our subject sequence and the query sequence below. Instead of sliding our query sequence to compare them, we can extract k-mers from both and look for exact matches between two sequences. This method of comparing exact k-mer matches is faster than traditional methods of alignment and is particularly useful in large-scale genomic analysis where speed and memory efficiency are critical. One of the challenges of using k-mers is that the number of unique k-mers increases exponentially with k. If you have k equal to 2, that would be 4 raised to 2, where the 4 represents the A, C, G, and T. If you have k equal to 6, the number of possible k-mers is 4096. With k equal to 8, this grows to 65,000. Which can be overwhelming for both memory and computational resources. This is where minimizers come into play, helping us reduce the complexity by focusing on just a small, representative set of k-mers. What is a minimizer? A minimizer is the smallest value of k-mer selected to represent a longer k-mer or a group of k-mers. More like k-mers of k-mers. Minimizers allow us to reduce both memory consumption and runtime when processing genomic data without losing much accuracy. To find minimizers, we need to define two parameters, the W, which is the number of adjacent k-mers, or the window, and K, the length of the potential minimizer. Let's go through the steps using a numeric example. We used the numbers 0, 1, 2, and 3 to represent the nucleotides T, C, G, and A. Assume that we want to find among 4 adjacent k-mers, or the W, minimizers with length of 3, which is the K. We then divide the sequences into subsequences, here termed as L-mers, with the length L, where length L is the sum of W and K minus 1. The right-hand side shows the subsequences with length 6, or the L-mers. Each L-mer will then be divided into k-mers, in this case with a length of 3, after which we sort them lexicographically. The smallest or the first k-mer is our minimizer for this particular subsequence or L-mer. By doing this to these 10 L-mers, we find 4 minimizers to represent them. Now that we've covered the theory, let's switch to the notebook to see minimizers in action. I have a script that calculates minimizers for different parameter settings. Here's what happens when we use the default values of W and K. The minimizers are selected for the sequence based on these parameters. Now let's change the value of W from 4 to 6 to see how the minimizer selection changes. By increasing the window size, we end up selecting fewer minimizers, which reduces the memory usage while still representing the sequence efficiently. You can play around the parameters and see how it affects the resulting minimizers. To wrap things up, k-mers are powerful for sequence comparison, but their exponential complexity makes them difficult to manage at times. Minimizers offer a practical solution by reducing the number of k-mers we need to store and compute, while still maintaining the accuracy of the data analysis. Thank you for watching. If you have any topics you want me to discuss, feel free to comment down below. See you in the next video.